Welcome to this explainer. Look, if you've ever fine-tuned a large language model, you've probably hit that totally frustrating wall where your highly capable model suddenly turns, well, rigid. Today, we are unpacking our really fascinating paper on exactly why our AI models lose their creativity during fine-tuning, and we're going to break down the elegant math designed to fix it. Let's get right into it. Let's start with a bit of a mystery. You feed a model this incredibly rich, diverse supervised data, right? But the second you align it to human preferences for tasks like writing or brainstorming, boom, the creative spark just vanishes. Why do they suddenly sound so robotic, repetitive, and just downright generic? Well, that right there is what we call the alignment paradox. It's the super frustrating trade-off. Standard reinforcement learning from human feedback, or RLHF, absolutely makes our models safer and undeniably more helpful. But the cost? It severely narrows their focus. They get really good at following the rules, but in doing so, they completely lose their creative Spartan output, diversity. They just learn to play it safe over and over again. So here is our roadmap for today. First, we'll unpack the alignment paradox. Second, we'll diagnose policy contraction. Third, we'll introduce CAPPO. And finally, we'll look at the actual data for better models and broader support. All right, Section 1, the alignment paradox and the hidden cost of RLHF. So what does this hidden cost actually look like under the hood? Basically, practitioners see this massive drop in output diversity. It's almost like the model develops severe tunnel vision, hyperfixating on just a few high-reward modes. The symptoms of this on-policy distributional drift are stark. Per token entropy, which is essentially our statistical measure of word variety, just tanks. Repetitions shoot up, and those perfectly plausible creative alternatives the model used to know, they suddenly get vanishingly small probabilities. All the probability mass shifts entirely onto a tiny subset of safe, high-reward outputs. Moving on to Section 2, diagnosing policy contraction. Time to name the culprit and actually measure the loss. If we're going to fix this tunnel vision, we need a formal name for it. The researchers call it policy contraction. Literally, the model is forgetting perfectly good alternative answers as it trains. Its support progressively narrows, and probability mass concentrates on a shrinking set of completions. Think of it like a student who memorizes one highly rewarded way to answer a test question and totally unlearns all the other valid creative ways to express that exact same answer. Now, how do we actually measure this without relying on messy decoding tricks like endlessly tweaking temperature or top P settings? They introduce a really rock-solid metric, the support retention ratio, or SRR. This metric tracks exactly how much of the original supervised data survives the RLHF gauntlet. It's just the fraction of supervised completions that retain a non-negligible probability under the newly trained policy. Basically, it's a direct gauge of how much of its original vocabulary and style the model kept. And the visual proof of the standard PPO collapse is wild. When you look at standard PPO's entropy as training updates increase, the exploratory diversity just dives straight down. Then, looking at the log likelihood distribution shift, you get this squeezed bell curve that perfectly illustrates the tunnel vision. The mass just shifts sharply. The model is literally shedding its viable options right before our eyes. Which brings us to Section 3, introducing CAPPO, Contraction-Aware Proximal Policy Optimization. So how do we actually fix this brittle tug-of-war between achieving high rewards and maintaining high diversity? Well, standard PPO kind of treats diversity as an afterthought. It uses this brittle scalarization with fixed weights, meaning reward is king, and entropy and KL divergence, which just measures how far the model strays from its original behavior, are just minor penalties. But CAP PPO, it completely rewrites the rules. It reinterprets reward, entropy, and KL to reference as equal pure objectives. It uses Pareto mixing to create a win-win scenario, so progress on the reward doesn't have to trigger an entropy collapse. Under the hood, CAPPO relies on a few brilliant mechanics. It uses minimum norm multigradient descent to approximate a Pareto improving step at each update. That's really just a fancy way of mathematically ensuring it finds a direction that improves one objective without tanking the others. But the real magic is its entropy scheduling controller. Think of it like an automatic thermostat for creativity. It dynamically injects exploration pressure when entropy starts to collapse and backs off when diversity is healthy. All right, Section 4, better models, broader support. Let's look at the empirical wins. When you actually test this on heavy hitters like Llama, Quen, and Mistral across multiple datasets, the macro averaged results are just wow. CAPPO doesn't just bump the preference win rate from 67.4% to 71.2%, it absolutely crushes the diversity problem. Self-Blue, which measures redundancy, drops from 0.48 to 0.33. Distinct 2 diversity jumps up, and the crown jewel, it recovers that support retention ratio, leaping from a super restrictive 0.55 under standard PPO to an incredible 0.82. Looking at the training dynamics over 50,000 updates really drives this home. Standard PPO just steadily kills exploration over time. It's a continuous, sad downward trend. But CPPO, it keeps that entropy line high and stable. The model is continuously learning human preferences, but, and this is key, it's not sacrificing its broad, creative vocabulary to do it. You see the exact same story with the support retention ratio. Standard PPO aggressively discards those reference completions, sinking lower and lower with every single update. Meanwhile, CAPPO consistently preserves over 90% of the original distribution support throughout the entire 50,000 update run. It literally escapes policy contraction. Now, I know what you're thinking. What's the computational cost of all this fancy multi-objective math? Well, get this. You get all these massive performance and diversity gains for just a roughly 3.1% increase in peak memory overhead. Seriously, 3.1%. It is incredibly efficient, retaining up to 94% of the throughput of standard PPO. In the world of model training, that is practically a free lunch. CAPPO absolutely proves that alignment and creativity are not mutually exclusive. By elevating diversity to a first-class objective, we really can have our cake and eat it too. Which leaves us with a pretty exciting question. If you no longer have to sacrifice creativity for safety and alignment, what kind of wildly capable, truly adaptable model are you going to build next? Thank you so much for joining me on this explainer, and I hope this sparks some amazing ideas for your next training run.